In the theory of probability, we are working with so-called random experiments. Random experiments. Why do we say that they are random experiments? And what are the criteria of the random experiments? Firstly, random experiments, they give unpredictable results. First of all, they give unpredictable, or we can say it random result, an unpredictable or random result. For example, if you try to measure somebody's height, you can get any result between 50 centimeters and 2 meter and 50 centimeters. Because we don't have anybody who is beyond these two boundaries of the height of the human beings. I think you've never met people with heights more than 250 centimeters. I very doubt if you met somebody who has heights more than 2 meters and 30 centimeters, but I know that the highest man all across the world has about 255-60 centimeters. And so, what does it mean? I did it by design this example. Unpredictable result, but it's limited by some boundaries. Some interval. So result within some interval. This interval we know like outcome. We say it not even outcome, but outcomes. Not only one. So we can say that set of outcomes defines results of the random experiment, as I said. So clear that random experiment has two very basic traits. The first one, result of the random experiment is unpredictable, but we can define the limit of all of these results. The closed limit, I mean. Examples. Heights of human beings between 50 centimeters and 255 centimeters. Nobody has less than 50 centimeters and more than 255. So it is restricted. For example, dice tossing. All results, they are limited. I can't predict really if I have 2 or 3 or 5, I don't know. But I know that I have exactly between 1 and 6. 3, 4, 5, 6. So I have limited outcomes and what? And unpredictable a particular result. For example, temperature, outside temperature. In our country, it can be between minus maybe 55 plus 55 degrees Celsius. I can say exactly what temperature will we have tomorrow, but I can say that it is between these two numbers. Okay. That's why we can add up most of all the problems and all the theory of probability, adapt to the set analysis, and that's why we can train our skills in set theory and operation with sets. Okay. Because so we have here outcomes. I put here, I outline them using the ink. But we have sometimes the other situation when we consider events. What is it, event? Event is a combination of the outcomes, made up combination. For example, if I am very interested in 3 and 4 outcome of dice tossing, because maybe I bet on 3 and 4 to get a good price, I consider the event here, example of event 3, 4. So it's part of these outcomes, but it's made up. For example, I want to know if we have tomorrow a temperature above 0, because I concern myself about some water vessel outside of the outside, and I'm bothering about the vessel, because you know that water, if it is freezing, it is kind of stretching and destroy the vessel, and that's why I'm kind of bothering about it. So you can see that outcomes, they are like stricted boundaries of outcomes. Here you get 1, 2, 3 examples, and event, it's kind of made up situation. Maybe you are very interested in this situation, I don't know why. Okay, so that's why we are working with set theory. In our sets, using the capital letters S, A, B sets, and using small letters S, A, B, I denote elements of set. So I can say that set is a family of the objects with the same features, same features. Okay. I can use some logic operations with set. So I can use AND operation, S and B, for example. It includes all elements which belong to A and B at the same time. The visual interpretation of this operation, I can built using so-called Venn diagrams. This curve, it is S and B, another one curve, another one shape B, and this shaded part shows you the elements which belongs to the S and to the B simultaneously. So this thing is S and B operation, and they use word and operation. This is the first one. The second one. S unites B or operation here. Or operation. Usually the work here includes all elements which belong to A and all elements which belongs to B to B and to S, as I used S and B. If I use so-called Venn diagram, so the shaded part here, the whole space of S and B. What else do we have here? Usually, as I say, S we use for space, as it is space set which includes all sets. All sets. So we can make this the third one picture here. I can this is S, and all sets, they can be A set, B set, for example D set, as it is space set, GBA, they all of them belong to now they are set, all of them belong to the S set. So this is the Venn diagram here. Okay. Firstly, let's make some example with the Venn diagram. Venn diagram. Example. For example, we have A and U and A or B or C equal let's prove this one. So first one example, let's prove that A or B or C equal A or, and here we have B and or U like separately. These parentheses, they show the order operation. So it means that if I make firstly operation between A and B and then with C, I have the same result if I have made the first as a first operation B or C operation. Let's make it. For example, I have A, B, and C. So you can make this graph diagram arbitrary as you want. So you have A here, B here, and C here, and we have make all operation or unite. This sign means unite. We have all of these one. Firstly, I have to unite A and B. I have this one thing, and then I add C part to this operation. And the same thing I have here. Firstly, I have to unite B and C operation, and then I have to add A here, and I still have the same shape, the same result. And next example. For example, I want more complex situation. Look, this is the first one. The second example, I have this operation given. Prove. Verify that A equal the second one example, I have the more complicated situation than the previous one. So I have here B and C or A. Here I have A or B and A or C operation. To prove it, I have to make two visualization, two diagram for the first one case and for the second one case, using the same shapes. I have here as the first operation within parentheses B and C. B and C, it is this one piece. It is B here, here C, and here I have B and C. And now I don't know, I can put here A arbitrary, it doesn't matter how I do it. This is, for example, this is A. And I have united here with the AND operation between B and C. By the way, AND operation, I can say it's like here you have unite, and here you have intersect. Look. What does it mean? So I have to unite A and this one piece of intersection. So this is A and this one small piece. This is sketched by ink, drawn by ink, red ink. Shape is a result of this operation. It is A unites joins B and C. Okay. This is the left part. What about this one? So I have to make the same ones shapes. They are B, they are C, and here I have A. I have to make separately. First I have to unite A and B. I have here A. I use the same red ink, and it gives me with this one, and unite B with this one piece. And then I have to make the same operation with C. I use the green one, A separately. Okay. And now I have to make this intersection between red part and green part. And this intersection I can draw with blue ink. Intersection between green one and red one. This part and this one. And you compare this result and this result, you can notice that the red shape and the blue shape, they are the same set. I use special green ink here. And you can notice that they are equal because we have the same bulb with this one appendix here. The same bulb, this appendix. Okay, I can use him to shade it there. Okay, so this is the very short instruction how we can use the Venn diagram to sort out the so-called the set operations. By the way, so we have here as a or unite and here we have and intersect. Intersection. Okay.